Okay, well, this is the last amine lecture, presumably the last amine lecture before the exam. And hopefully on Wednesday I'll do some things. I'm always open on Wednesday to problems that you may be having and try and answer those. In the meantime, can you do that problem? What do you think about that problem? Could there be a problem like this on the next exam? There is going to be a problem like this on the next exam. So can you work it? Can you write down a solution to this on a piece of paper, and I will come over and look at it? No paper, we only need one sheet. He's got a backpack. Do you have a piece of paper? You have a solution. How about it, you guys? Anyone got anything? You have something? Good. Chlorination, bromination. That looks a possibility. Chlorinate followed by bromination. What about that? Well, you know, this happens every year. The students kind of, the excitement that we see in the fall is not quite there. And I don't see too much activity on this. Few answers. How about you got an answer? You got a piece of paper anyway. So what do we have to do? Here we have toluene. We need to introduce a bromine. We need to introduce a chlorine. How do you do it? How do you introduce a chlorine? How do you introduce a bromine? Well, let's see. There's some possibilities. Pick the one you like. What do you think? Okay, got your answers in? Oh, no, I guess not. This is it, the last lecture on amines before the exam. And there is going to be a little mini synthesis. Like this, maybe like this, but it's going to be like something. It's going to be, how do you take A to B? That's what we have here. How would you do that? What's that? They could all be wrong. Then I need, okay, A, B, C, D, E. None of these. What do you think? None of these? How does that sound? It's always nice to have that on an exam for an instructor because it gives us a way to bailing. Unfortunately, it caused a lot of confusion. All right, let's put up the 10-second clock and let's go with this. Okay. And the answer was B. Most people like B. 68% like B. What in the world is B? That's B? It's not B, you say. Well, you are going to have to, yeah, I'm going to have to choose B. 68% chose B. How can we not choose that? Yeah, of course, of course. Discussions are always welcome in this course. Always welcome. Best to discuss it with your friends and convince them first. Okay, so the answer was B. Why is it not bromination followed by chlorination? Why is A no good? Anyone got a good answer for that? Let's see, maybe. Okay. It's the old guy. You better have the right answer. What's wrong?
Well, when you add that chlorine, it would want to go ortho to the strongest activator, which would actually be the methyl.
Is that correct? Absolutely, that's correct. So that clearly is not going to work. What he said is that he said that if when we brominate, we're going to go para, but now when we chlorinate, are we going to go ortho to the bromine, or are we going to go ortho to the methyl group? Which one are we going to do? Ortho to the bromine, ortho to the methyl group? He said ortho to the methyl group. Both of these, however, do you remember, both of them are ortho-para directors. They're both ortho-para directors, but he said that the methyl group is a greater activator of the aromatic ring, and therefore it directs the incoming chlorination ortho to the methyl group. And so the chlorine would actually go in up there. And of course, that's completely correct. It goes in here, and it does not give what we could have had. Okay, let me just go back there. Okay, so, and that's going to be exactly the same thing down here for D. They're both bad choices because of the fact that the methyl group dominates the activation. So we knocked both of those out. Now we're down to these two. Now most of you said, why didn't you like C? Why don't you like C? Here, you guys didn't choose C, right? Why didn't you like C? Okay. What's wrong with C?
Well, you would have the chlorine in the wrong place.
Exactly correct. He says, look, that's ridiculous. What's wrong with C is the very first step. What happens is if you try and do the chlorination, what would you get? You would get the parachlorine, or some of the ortho as well. But para, you're never going to get the metachlorine. So that was, even though there's a lot of stuff in there, you didn't have to do it because you know that the first step is wrong. So that brings us down to B. Can we have a conversation about B? Well, let's see. First step, nitration. Okay, you're going to get para. You're going to get some ortho. Actually, para dominates. Para probably dominates for steric reasons. Not always, but in this case, I believe it does dominate. You're going to get the para-nitrotoluene. What's the next step? Catalytic hydrogenation. What is catalytic hydrogenation going to do? It's going to take the amino group, the nitro group, convert it into an amino group. Now, what happens when we chlorinate? We take chlorine. Oh, I think I may see what someone may think is a problem. You don't like that chlorination. Why? Okay, that's a good thing to discuss. When we chlorinate the nitrotoluene, you think what's going to happen?
It's going to double chlorinate because the amine is really strong.
That's a good point. I was thinking something else. No, that's a good point, though. What she's saying, she's saying the amino group is an incredibly good activator, and that's something to keep in mind. Amino groups are whenever you see an amino group in your life as biologists, when you see an amino group or a hydroxyl group on an aromatic ring, think of it. That aromatic ring is bubbling off its electrons. It's very, very nucleophilic and very reactive. It's easily oxidized. When you see that, and you'll oftentimes see in biology these aromatic rings being oxidized, the ones that are easiest oxidized are the ones that have amino groups and hydroxyl groups. Anyway, so that could be a problem, but we're going to, for 321, that's not a problem. Chlorination goes in. And where is it going to go in? Ortho or ortho to the amino group or ortho to the methyl group? Let me ask these guys over here. How about one of you guys? Ortho to the amino, or why ortho to the amino?
Because it's strongly activating and it'll go right next to it?
Yeah, it's strongly activating. It's dominating the methyl group. We just reversed that. Absolutely correct. So we're pretty good now. We now have to convert the amino group into a bromine. Well, that's not going to be too difficult. We do the nitrisation, we make the diazonium salt, followed by copper bromide, and sure enough, right up there in one sort of continuous step. Okay, so that's a good synthesis. You ready for another one? Could you do another one of these? What about the next one? Could you do that one? This looks really, really tricky. We've got the 3 halogens in a row. How in the world would you do that? How would you get those 3 halogens in a row? Any thoughts? How would you introduce 3 halogens? Well, you say, look, here's the fluorine. The fluorine's a little tricky because you cannot introduce fluorine by direct fluorination. In general, you can't do that. So it is a little on the tricky side. So we put that in, well, we're going to put that in by a diazonium salt. But what if we had fluorobenzene and we brought fluorochlorobenzene, we brominated it? Would it go in there? It's fluorine's an ortho-para director, ortho-para. How would we get the chlorine in? Chlorination. How would we get the fluorine in? We would do the diazonium salt. How does that synthesis look? Okay. What did I say here? What's wrong with this synthesis? What's wrong with this synthesis? It's not a good synthesis. Okay, excellent. Without twisting arms, we have a volunteer. Okay, yes.
You'll never get 3 that line up in a row like that. That's really unstable.
Yeah, well, that's true, what you're saying. You're saying they're very unstable because of steric effects. That's true. It's going to be less stable, but it's not very unstable. You probably could make this. No, but what is wrong? So we can, that scheme, there's something wrong with that scheme for making what we want to make. What we want to make is fine. We can make it. I don't have any doubt about that. But what you said, sterically hindering, it's going to want to rearrange. Okay, Mike, we got another volunteer. Okay, what is wrong with this synthesis?
It would rather go para than ortho.
Exactly, we just went through that, right? Yeah, it'd rather go para. So you're going to get the para compound in both cases. And so as a consequence, you're going to get a horrible mixture. Would you get some of this? Yes. You wouldn't get a whole lot for the reason she mentioned, because it's unstable. You don't want to put 3 halogens in a row. So these are, oh, maybe that's what you were saying. Oh, I just misunderstood you. Yeah, you know, you jumped ahead on me. Yeah, okay. Of course you say you're going to get it where they aren't all in a row. So she was absolutely correct the first time. I misunderstood her answer. Thought she said it couldn't be made because it's unstable. Okay, but what's right with this synthesis? What is the good part about this synthesis? This is not a good reaction. That's not a good reaction. What's right about it is it's a way of introducing the fluorine. This is a good step. So we want to keep that step. We want to keep the fluorination step in this synthesis. But how in the world are we going to direct it there? Well, as someone mentioned earlier, let's block the para position. And that's a good strategy. But whatever we block the para position with, we've got to be able to get rid of it. And there aren't a whole lot of things that will do that. Okay, so we'll keep the good step, the fluorination. Tell me. Here's what I need to do now. I need to introduce a blocking group. But I need to introduce a blocking group that will then allow me to brominate and halogenate these 2 positions. How would I introduce a blocking group, or what a blocking group? We have another volunteer from the far left. What blocking group would you suggest?
Put N2 on there. Make it a diazonium something.
Okay, he said, let's stick a diazonium salt down here. Why? Can you convert the diazonium salt to a hydrogen? Yeah. And you say, yes. It's one of these reactions up here. Up there. Oh, hey, I better tell you this, guys. Those of you who looked on the cover, I don't have those reactions on the cover. If you think you're going to need them, you better put them on your card. They're not on the cover. The cover is up, and I only added one synthetic reaction to the cover for what I call the one synthesis. This kind of stuff I wouldn't call synthesis because we give you the reactant, we give you the product. Okay. You have a question? Yeah. Or a suggestion here? Go ahead.
If you put an N2 for a blocking group, then you're going to get a reaction with the halogen, so it's better to just leave an NO2.
Yeah. What he said is correct, is that you probably, the N2 ultimately we're going to need to come as a, we're going to need the N2, but what we need to do is block it with something other than the N2. He said, but those halogens will react with N2, and that's probably correct. And so how, well, let's go back to this guy here. How do you introduce how do we make a diazonium salt? Do you remember how you make those diazonium salts? What is the first thing you're going to do to fluorobenzene to ultimately end up with a diazonium salt?
You have to make it NH2, and then you have to introduce
That's right.
NO2.
You got it. You need, what he said, we need an NH2 here. We need an NH2 again, because you saw that just before. We need an NH2. Do you know any way of taking fluorobenzene and making an NH2 group directly? You don't know any way directly, but you also gave me the indirect method. You said what you're going to do first is you're going to nitrate. You're going to nitrate, and then you're going to reduce to the... oh, no, sorry. Ultimately, we're going to reduce. But we are all set up now. We don't want to reduce yet because we get the amino group down there, and it's going to direct orthopara. So we'll keep it like this, put in our chlorination. The fluorine is a more activating group than is the nitro group, but it doesn't even matter. They both ortho. This directs ortho. This guy directs meta, and it all goes in right there. Goes right into that position there. There's the chlorine, there's the bromine, and knock it off by the reduction that you mentioned. Okay, so that is synthesis involving these diazonium salts. These problems are a lot of fun to do, I think, because there's all kinds of possibilities, and indeed they are used in chemistry to introduce various halogens. In fact, well, they're used in biology. Yeah, you have a question? Yeah, just a second. Question for everyone.
When you have an NO2 and an F, aren't those both deactivating groups? So wouldn't you want to not add the Cl? Like, wouldn't you want an activating group to be on the ring before you add the Cl?
Okay, the first thing you said is true. Aren't the fluorine and the nitro group both deactivators? And they are, because they're both electronegative. Now, we already know that the nitro group will direct to the meta position. And so that's good. That's going to help us out. Now, where does the fluorine direct? Does it also direct to the meta position? Does it do that? Or does it direct to the ortho position? It directs to the ortho position, exactly, because it moves the pair of electrons in like that, and you can imagine the pair comes out like that, directs it right to the ortho position. So both of these direct to the same position. And so as a consequence, you get the chlorination going in there. They both do exactly the same thing again, deactivator, activator, and it goes in there. Oh, are you talking here? I lost. I may have misunderstood another answer. Were you asking about this chlorine here? Is that the one you were talking about? Okay, go on.
I was just wondering why you don't change the NO2 to NH2 before.
Oh, the NO2 to NH2. Well, we will eventually, and that's what we did. No, but that wouldn't help you here. But it is possible. You might say, doesn't this chlorine here want to direct to that position and that position? That's a possibility. But the fluorine, something you don't know, but we're actually getting help here. See, if you direct to this position, you're interfering with that guy. But it also turns out fluorine is a better electron donor because it's of the same, electrons are at the same level. Okay, we all on board with this? We good on this? Okay. Oh, yeah, forgot about that. We got a review. The review is going to be tomorrow, 6:50 to 9. And in principle, they always say they're going to have the echo. They claim they are going to have the echo up there. And you have a question?
Yeah. Could you go back to the previous slide, please, for a second?
I can do that. Let me see if there's any question about where you're going to. There's going to be this review. My understanding, you guys are doing it again, the undergrads. Do you know? You don't know? Okay. I think they're all organized to do it. And in the past, all I can say, I don't know what this one's going to be like. In the past, I've thought they've been very good. Now, remember, the advantage is there are undergraduates, many undergraduates doing it. You may have to be a little patient, but they took the exam previously, and they got A's on these exams previously. And so listen to what they're saying. From the point of view, they're like you, except they've gone through the exam already. Okay, now this guy wanted to go back here, and hey, I'm back there. You ready for your question? It's hard to keep you guys focused here in the morning. Everyone, such a beautiful day.
My question is, when you nitrate it, before you reduce it to NH2, couldn't you just brominate it and chlorinate it, and then reduce it, and then add the fluorine instead of renitrating?
Oh, let me see. He has an alternate synthesis. I better stay back here with you. He has an alternate synthesis that's up for discussion. Where are you? Where you're with the? Okay. You're way up here. Okay, so we've got the nitro. I mean, this is the kind of stuff we see on the exams all the time, alternates to what we've done, and we have to grade those. So this is an excellent opportunity to evaluate an answer. There's the nitro group. What do you want to do?
And then chlorinate it and brominate it.
Okay, chlorinate. I'm going to go shorthand. Brominate. And what he's going to end up with is this guy here. And he's going to end up chlorinate. Where's the chlorine going to go? It's going to go in the meta position. So it's going to come down here. The chlorine's going to come down here. Now what are you going to do next? Reduce the NO2 group. I'm running out of room here. Reduce the NO2 group to, and then what? Give me the whole thing so I can.
And then attack it with the HBF4.
Okay. So he's going to reduce it, convert it to the diazonium salt. I won't put the reagents since they're up there. And so he's going to end up with a diazonium salt, right? Or you want an amino group?
So then you have an NH, so that's reduced. Yeah, that, right. And then you have a fluorine on the bottom, right?
We need a fluorine. How are we going to get it?
Well, with the NH2, right, so it's a strong activator. So the fluorine would go at the pair position.
Okay. Okay, the question is, how do you get the fluorine in there? Now, he said to directly fluorinate, but we said you can't do that. But the question is, could we actually, at this point, nitrate? Could we introduce the nitrate down at this position? Because that is a very powerful activator. So could we end up getting a nitro group down here? We got an amino group here, and we got bromine here and chlorine there. The nitro group, we know we can convert into a fluorine. So what we would have to do is get rid of that guy by the diazonium stuff here, then reduce that and convert it into a fluorine. Could you do that? That was kind of your, it wasn't exactly your question, but you can't directly fluorinate. The way you would get the fluorine in it is to nitrate and then convert it. I just ran out of room, but can you see what he wants to do here? He wants to take this to a hydrogen, Let's take that to a hydrogen using this particular method here, and then he wants to use that diazonium process up here. So, oh, geez, this is a mess. To get, you know, it looks like that would work. Is it full credit? It's a little long. That's the only thing. Is it full credit? You know, it's in the, whenever, since there's a better method, it always presents the graders with a problem. Certainly at the beginning of the course, if we get two answers that aren't quite identical but look equally good, we give credit to both. Here, I'm not sure. I don't have a good answer for that. Would it work? It looks like it might work. Some problems, but it looks like it might work. So, okay. Yeah. Now we're at the place I wanted to be last time. Are there other reactions of diazonium salts? Yes, there are lots of them. There's one reaction in the textbook I haven't talked about. Do you remember what that reaction is? It's the reaction with aromatic rings that have strong activating groups. Hydroxide. What's another strong activating group? Amino. And so my question is, what is the product of this reaction here? You can imagine various things. What is the product of this reaction? I'm going to simplify it and give you a choice of only 3. Oh, jeez.
We know the answer.
Well, that's okay. Let's see if you do know the answer. Use common sense. What I didn't give you is, some of you may have thought, and I think it's legitimate to think, is that I will have the oxygen attack or attack there. You notice I didn't give any of those as possibilities. So that's not what's happening. Okay. This reaction, incidentally, you talk about the social impact of this reaction. It is massive. This is one of those, it's hard, the world you live in, science plays a very important role. In the 19th century, science did not play an important role. It is this kind of chemistry that all of a sudden brought science to the forefront of commerce. Commerce, trading, making money. How can you make a lot of money off that reaction? That's the challenge. Can you tell me, where is the money to be made in this reaction? Okay, let's end this. Enough. This kind of stuff showed society that a little bit of knowledge, yeah, of course. Yeah, it was that one. Now, the product of this reaction is that guy there. Here is my challenge. Is there anyone here that can tell me the importance of this reaction? And this is a very general reaction. The stuff that you make via this reaction changed your lives dramatically. In fact, if you look at old pictures of the 19th century, what is it you notice about the 19th century? Well, let's go back a little bit before that. Ah, Michael has an answer to this. What is it?
I think it's color in photographs.
Color. It's exactly correct. Michael, that was brilliant. What he said, dyes. That's what these things are. You change the substituents. You can change the color. You make these dyes that color fabrics. You see these old photographs. Everyone is sort of brown and gray. And it just wasn't black and white photographs. That's the way it was. That's the clothing. They didn't have colored things. You probably may, in the book, they talk about this Tyrrhenian purple or alizarin, not alizarin, what's the other one? The one from India. Indigo. Indigo. Tyrrhenian purple comes from a shellfish, indigo. The only people that wear purple were royalty. And look at, we see all kinds of blues and purple in here. All of a sudden, for pennies, you could make a dye that gave you colorful stuff, such as clothes. That was really, really important. Vegetable dyes just wasn't enough variation. Okay. However, at the beginning of the lecture last time, I said this reaction saved my life. Why did this reaction save my life? It did. It literally did. I was no bigger than this. It was in my first year of birth, and I got saved. And some of you may have been saved by the same kind of, what is it? What is it that saved me? Do you remember what I said it was last time?
Antibiotics.
Antibiotics. Again, something that you don't, that we tend not to appreciate today because they're so available. Bacterial infections resulted in huge numbers of deaths. And it turns out, what role did azo dyes play in medicine? You already told me. They are antibiotics. I don't know if you read the story in your textbook, a really interesting story. I think it's interesting. You know, you're going to be parents someday. Here's this guy. He had his daughter. She was 10 years old, I believe. She got a pinprick. Something as minor as a pinprick infected. She got infected from that, and then she got infected, and she's dying. What does this guy do? He happened to work at Bayer at that particular time, where they had been working on these sulfur drugs. That is, these dye compounds. And there's so much cultural stuff here, it's hard to imagine. It turned out that some of the early biologists thought that the dyes that they used to stain, you do these in biology, you stain various specimens with dyes. They thought these must be drugs somehow. So this was a hypothesis, crazy hypothesis. I mean, why would they think that? Anyway, they thought that dyes may be drugs. They may be magic bullets. So they just started testing drugs for all of these diseases. Well, by chance, one of them killed bacteria. And so it worked on the mice, and this guy knew that his daughter was sick, and so he got this dye, and it's this one, Prontosil, and that was going to be my quiz. We'll still do the quiz. I thought I had the picture of the dye. This dye is red. Prontosil is red, and he fed 10 grams of this dye to his daughter. I mean, I can't imagine. She must have turned red with that much dye in her. But she lived. 10 grams is a lot. Who would take 10 grams of any antibiotic? But she lived, and boy, there was just a revolution. Antibiotics are so powerful today, and they're so cheap, and they're so easy to make. Mainly we use penicillins, but they still use sulfur drugs for TB, some versions of TB. Just an amazing story, I think. The two things, color, dyes, and then the antibiotic came out of that one single reaction, which in a sense you might not think is terribly interesting, but the cultural impact of that has been immense. That's why we talk about it in organic. Okay, why don't you do this one for me? What do you think? We got to run this forward. Now you got to use a little common sense. It's only two possibilities. Both the same reaction. Which one looks good to you? And so this is the kind of stuff you want to bring into the exam on Wednesday. Common sense. Sometimes we call it intuition. Sometimes knowledge. Whatever. What would you do? Let's see how we come up with this. One of these would work, I know. The other one I don't think works, but I don't know that for sure. I just don't think it would work. Okay. Well, 10-second clock. Second what? Oh, yeah, you weren't talking to me. That's fine. Okay, whoa, whoa, even tie. Most of you like A. A few of you like B. 43% actually. Ah, would anyone like to defend their choice? Anyone chose, who chose A? Anyone chose A? Why did you like A?
Well, I was looking at B at first because it was similar to that last problem, but I think the sulfur group is like a deactivator, so it would add on the meta instead of the para. So I figured in A, you're looking at the NH2, which is an activator, so then that would add on the para position, so I chose A instead of B.
I couldn't have said it better. You heard what he said. He said that sulfonyl group. Look, what you have to say is, what is this? This is an electrophilic aromatic a reaction of the electrophilic aromatic substitution. Only this is your electrophile. And he's saying this is an electrophile attacking that ring. He has to evaluate that substituent. He says that I don't know what that substituent is, but it's got to be at least an electron withdrawing group, sulfur with carbon with oxygen bonds attached to it. Yes, the sulfonamide is an electron withdrawing group. If it's an electron withdrawing group, it's not going to be an orthopara director, which you need here. It's going to be a meta director. That by itself is enough to totally kill B, and the correct answer is, of course, A. Because look at that activation. Talk about activation. You have 2 amino groups on there. Tremendously activated ring. And so as a consequence, this reaction should be very fast. This reaction, I can't believe even occurs, even though I don't know that for sure. OK, so I go with A. A is for sure the best choice there in the absence of no information. OK, so we got that. Prontosil. Oh, how do they work? Well, let me just tell you, this is the amazing thing. It turns out we put all this garbage on there, made these dyes, and it was the... See, remember, the hypothesis was by the biologist, Ehrlich, thought that dyes, since they stain tissue, they must be reacting with the tissue and therefore could be drugs to cure disease. I don't think that's a good hypothesis, but it worked in terms of developing antibiotics. So here they have these dyes. It turns out it's not the dye at all that's the important component. What is it? It's the sulfonamide. These guys, oh yeah, that's what I wanted before. I don't know whether this is true. That certainly looks like a vial that they could have had back in the 19th century containing, there's the dye down there. It wasn't the dye at all. You take the dye. The dye was just a prodrug. What is a prodrug? We all take prodrugs. A prodrug is something that's converted into an active agent. What is that active agent? It turns out that the metabolism of the dye produces sulfonamide, which by itself you might say, well, why is that biologically active? Looks pretty common. Well, it turns out your enzymes, not your enzymes, the enzymes of bacteria think that that looks like para-aminobenzoic acid. And para-aminobenzoic acid in bacteria is a critical element for their survival, and because they convert it into folic acid. And if the bacteria have their enzymes swamped with this guy, it competitively inhibits the formation of folic acid. And as a consequence, the bacteria die because they can't make the folic acid. So how this operates is very, very typical of modern drugs. But the development of it as an important drug was more obscure. Now, it turns out at the same time we were developing sulfur drugs, we developed penicillins. So the sulfur drugs didn't have the impact that they might have had if we didn't get the penicillins in place. OK, so I think that kind of ends the diazonium. Oh, yeah, I just grabbed this off Wikipedia. OK. Stay with diazonium salts. What's X? What is X? Here is a diazonium salt. We're going to warm it up. When we warm it up, we're going to get two products. Can anyone name one of those products? Anyone want to? We're going to get three products. Can you give me the name of one of these products? Anyone want to volunteer a name? Ah, great. Hey, I thought you were on the balcony. You move around. Okay. Actually, it's kind of hard to get in here. What one of the products?
Carbon dioxide.
Carbon dioxide. When you're right, you're right. That was the hard one. How about you guys? There's another product. Carbon dioxide. Well, we'll say, just make a guess. What do you think the next product is? You can get help from him.
Is it carbon? Nitrogen.
Nitrogen.
Exactly correct. Exactly. Okay. What did they say? Carbon dioxide, nitrogen. What is X? What is X? Is that the row back there ready for X? Okay. No. Okay. Work through it. What's going to happen when you lose carbon dioxide and nitrogen? What is left behind? What is left behind? What do you think? What's left behind? Yell it out.
Benzene.
Okay. Do you agree? Make your choice. Don't let me down on this one. Common sense. Use your common sense. That is, use your bond making and bond breaking stuff. You need a piece of paper, Anna. No paper. You worked it out? Which one do you like? You knew that? Okay. You got an answer on this one? No. I wouldn't choose that one. Okay, how's my group back here doing? You guys good? What do you like? It's not in the book. I don't know where you got that answer. But you're right. Okay, let's end this. I hope you got that through nice common sense. Common sense. Okay, a bunch of people chose B. Well, let's look at this. Let's look at this. Look, that nitrogen wants that pair of electrons. But that's going to cause that carbon to get a positive charge. Hey, wait a minute, but we got a negative charge up here, and we make carbon dioxide anyway. So what if we just do this? So we get off carbon dioxide, nitrogen, leaving behind X. What would X be? Well, X would have to be the way I've shown it. It would have to have a positive charge there and a negative charge here. What was the correct answer? Yeah, exactly. The correct answer has to be what you all chose. It has to be that one. I think that's pretty good. Okay, so the correct answer was, oh gosh, I missed well, can't do that. Okay, so you make this benzyne, and it turns out this is incredibly reactive. You cannot put this in a bottle. It is a reactive intermediate. And as a consequence, you can put a reactant near it or when you're doing this decomposition, and it will react, and it gives you this compound here. That compound is a Diels-Alder reaction. Okay? So that ends, I think, my diazonium salt stuff. Benzyne undergoes a Diels-Alder reaction. So, like so. Now, do you have to forget the Diels-Alder reaction for this next exam? Can the Diels-Alder reaction be on exam 3? Of course it can. The course is comprehensive. That is why the grade you get at the end on the final, we consider to be measuring your total knowledge of organic chemistry, because it's cumulative. Everything goes from the beginning to the end. Oh, sorry, I got one more of these. Thought we were going to get into new material today, but we aren't. Does that make sense? Here we have an amine. We treat it with the nitrosating agent. We make the diazonium salt. The diazonium salt is not going to be stable. It is going to decompose, and it's going to give a product. Could you write down on a piece of paper what this product is? That would be a great problem for the next exam. I could say, predict the product of this reaction. I could have done that for the benzyne one, too. I could do it for this one. Can you do that? You guys, can you tell me what the product is? Pretty tough to do without paper. Give the class a hint. What is going to be the next step? The diazonium salt is going to decompose. What is one of the products? How about the guy in the middle here? What is it? Consult. What is one of the products going to be? No, one of them. What's one of the products? Simple product.
Nitrogen.
Exactly. You guys aren't providing much help here. This is going to lose nitrogen, and it is going to leave behind what kind of a species? So when this goes, it's going to give nitrogen, and what is going to be left behind? What kind of a species? No, a carbon species, something containing carbon. What functional group is going to be left behind? Yeah, go ahead.
Carboanion?
Okay. He says a carbanion. A carbanion. You want to change that?
Carbocation.
Exactly. Look, it's positively charged. You lose a neutral, you get a plus. A carbocation. What can carbocations do? Oh, that's hard to see. Okay. She's doing it too? Exercise the brain cells. This is doing a practice lap around the track or down the pool. You get the microphone. It's easier. A question? A comment. That's okay. Make a comment. Help the class if you can.
Wouldn't the oxygen then attack the carbocation from an epoxide eventually?
Is that a possibility? Yes, that's a possibility. But that's not what happens ultimately. But it's logical. And that's what's important here. It made sense. The oxygen's a nucleophile. You have a carbocation. But it would give a highly strained epoxide ring. And that's not the product we get. There's something more favorable. More favorable than that. You don't have a piece of paper. Oh, what is it? Yell it out. What functional group is the product going to be? A what? She says a carbonyl group. No, I'm not going to say the whole thing. Carbonyl group. Why am I not going to say the whole thing? Because that's a quiz. Well, what is the answer? No, well, which one of those is correct? I could have had yours up there, but I should have put it up. Maybe because it was too logical, I didn't. Which one do you like? Does it make sense? So we had some discussion. It gives a carbocation, and someone said it gives a carbonyl group. And which one do you guys like? Okay. Okay, 10-second clock. And the answer is B. Excellent. Okay, last thing I want to discuss. Why do I want to discuss this? Because it's part of this. This is truly the last thing in this material. And so on Wednesday we can start fresh. Okay, how do you make these things? How do you make, this is just given the mechanism. Oh, goodness sake. Okay, tell you what. On Wednesday, what I'm going to have to do is go over this problem again. Let me do that. Let's quit now. On Wednesday, we will do a little bit more of the amine chapter. Okay, so see you there. What's that? Oh, we better put up the